Okay, this is going to be a another two-part video. I apologize, that was my cat pulling on the cord. So sorry for this. It's not such a big deal, I think. I mean, you'll view that video, and then we'll just pick up here on part B. All right. So getting back to homework 3. The solution to the problem 3 is 18%. And I think that, these vehicles, I mean, the real answer may be closer to 40%. I think part of it may be that the engine is more efficient. I'm not sure about that. I mean, in principle, it should have about the same efficiency, but it may have slightly higher. Because you're sort of starting with your fuel in a vapor form or gaseous form. So the engine may be a little bit more efficient. This tank size may be off. I mean, they may put larger tanks in, which means that you have to take up room somewhere else. A lot of people, especially out west, have done pickup conversions, where they put a tank in the back, and so they can have a much larger tank. So anyway, I mean, an actual vehicle, you can probably go further. Maybe you can go to a higher pressure than 3,000. But this gives you an idea of how to figure what the range of these vehicles is, which on the face of it sounds like, okay, that's going to be the problem here with natural gas vehicles. It's not so much the charging or the fill-up time, so to speak, because I think that can be similar. It's more complicated than the gasoline, at Wawa, but probably a similar time. If an infrastructure developed for natural gas vehicles, Wawa gas stations and stuff like that, it probably wouldn't be so much more of a challenge to fill up with a natural gas vehicle once you learned how to do it, and it probably could go pretty quickly. The only similar thing that I can think of right now that you may have experience with is filling up your propane tanks for your barbecue. I mean, and you don't actually generally do that. You hand it to the attendant and they do their thing. But it appears that the range is going to be somewhat of a challenge for these types of vehicles. All right, so let's move on. And what we're going to do now is we're going to do a review. All right, so the effect of my cat is to have made this video part A primarily the homework solution. So there's kind of a natural break point there. I don't think that was what my cat was thinking. And now the review. So energy systems. Quiz 1 review. So I kind of made up a chart, and the idea here is I'm going to kind of do a one board, two board thing. So the first board is kind of, let's think of it this way, calculations. And these are the equations we learned. We learned that energy is force times distance. And kinetic energy, which is kind of, we showed how with that original equation you get kinetic energy is 1/2 mv squared. By the way, the quiz is going to be multiple choice, and it may require you to do some very slight, really no derivations. I mean, maybe a few times you might have to plug into something, but no, you're not going to be doing, derivations. And the point is that I really can't ask you to do that because, I mean, of the format of how you're going to turn it in, which is you're going to have a set of questions with multiple choice, and you're going to give me a set of answers. Now, when you give me your answers, you can provide explanations, but I'm not going to make it a requirement. So since I'm not making it a requirement, the extensive derivations can't be allowed here. Anyway, moving on with the review, potential energy, right? And I'm just going to write that, and the best thing for that was homework 2, where you learned how to calculate, the potential energy, as you plunge the plunger, and for gravity, right, as we just discussed, I mean, this since the force of gravity doesn't change much going over 1,000. Actually, I just thought of that. I mean, for that well problem going down 7,000 meters, does the force of gravity change that much? It might a little bit. Okay, but for gravity problems, we usually assume the force of gravity is constant, so that comes out of the interval and it's just h. But anyway, I mean, I'll write it that way just so you know it. And we learned that pressure of a gas is force over distance over area, and so that folds into there that way, so that area times the dx becomes dv. I won't write it out. And we also learned, and probably relearned for a lot of you, that pressure is proportional to T over V. And we haven't done much with T. It's mainly that it goes as 1 over V, and we've used that. And so you might have to use that in the quiz. And we also learned that electrical power is current times voltage, which some of you also might have already known. All right, and then we kind of went off in our calculation section here. We went off into reactions that produce energy, and you did the homework problem where you burned alkanes, and you showed this. And what we learned is the energy released is equal to the total bond energy. The bond energy, I'll write it as bond energy, can't spell, of the products minus the bond energy of the reactants. Now you'll notice I haven't specified what type of reaction this is, and that's because this principle holds true for both chemical and nuclear reactions. For chemical reactions, it's molecular bond energies. And for nuclear, it's nucleus bond energy. And I won't draw it because I'll run out of room. Actually, maybe I can draw it over here. There's this wall here that I'm up against, but maybe I can get it in here. We showed this chart where, okay, atomic number, that from 1 to to 92, which is uranium. Okay, and it does this thing like that. This is the nuclear bond energy. So in the sun, this is hydrogen, and so once the sun fuses hydrogen to make helium, and so releases that much energy per reaction. And this slope is exaggerated. This is uranium, and so as we'll discuss in a minute, in a nuclear reactor, uranium reacts to produce lower nuclei through fission, and so you get that much reaction, or that much energy per reaction. All right, so so moving along in our sort of thing here in the calculation section, next is units, exclamation mark, and you know, you've been using them throughout the homework problems. You need to go from MKS, you know, to back and forth to BTUs, back and forth to horsepower, and possibly even to electron volts, you know, and be fluid about doing those conversions back and forth. And then basically, finally, as a subset of everything, particularly chemical, we were able to calculate energy of a fuel per mass or volume. Using our knowledge of chemical reaction bond energies and being able to perform whatever conversions are required. So that's kind of the quote-unquote calculations part of the thing. Now, I'm going to go over here and hopefully not mess up my focus. It seems to help wearing a solid shirt, because I think it looks for lines, and probably I should wear, ideally, I mean, I don't want this to turn into a uniform type thing, but probably ideally I would wear a kind of a gray shirt so that there's less contrast between myself and the board. But anyway, this is then kind of the knowledge part, and there will be questions on that too. Now, I mean, you're helped here because you have the notes and you're able to look them up. You know, and so in principle you can answer the questions looking up stuff. And so here I'm going to do it this way. I'm going to talk about oil and natural gas. So I'm going to categorize it that way, and you know, what you've been shown basically, you know, how this works is you have what are called conventional wells, vertical wells, I'm not sure how to write it here to capture everything, but you plunk down this well, and what's down there is under pressure, it comes gushing up, and these then have to be pressurized eventually over time. Raised with usually with water. By digging a well off to the side and dumping water down there, and then finally there's other techniques, including, you know, your second homework problem today, basically lifting it out of there. But you know, that's kind of the main thing there. And then there's however you want to call it, horizontal drilling in shale strata. I'll write it out. In oil, gas bearing shale. Now remember, the conventional well relied upon the oil or gas bearing strata to have undergone an upheaval, so that there's like a particular place down there where all the oil and gas has kind of flowed up to, with this cap of hard rock on the top. Here you don't need that. You just have some strata down there that you've identified contains oil and natural gas, and so you drill down and you use those magical, drill bits to go down and go sideways and go horizontally along the strata, plus fracking, hydraulic fracturing of the shale to allow the oil to flow. And the way to think about this is that this is what has been going on for 100 years, but it's becoming less and less, particularly in the United States. This is now the majority of U.S. oil production is through this horizontal drilling and strat and fracking. Okay, and then coal. All right, now we didn't talk much about how you mine coal, and we could, but it's just there's no. The point is, in discussing oil and natural gas, you have to understand these techniques for mining to understand what's going to happen in the future. For coal, the coal is up closer to the surface. You basically dig down and get it. It's a hard job no matter what. There's no sort of, there's no way you can put down a well of some sort and coal will come up or anything like that because it's a solid. So here, what I wanted you to mainly learn was that there's sort of these two paths that you can go on. You can generate electricity then goes into electric cars. Okay, or you can produce through chemistry processes, gasoline and diesel, to go into conventional internal combustion engine cars. All right, and so this is coal. All right. In the year 2050, are we going to be using any? Well, on the one hand, okay, and I told you don't use this as a parameter. Climate change by that point in time is probably going to be pretty horrible, and so it's probably likely on that basis we won't be. But on the other hand, your job here is to keep the energy system going, the U.S. energy machine going, and so it may be determined that, well, we simply can't function as a society unless we use these massive reserves of coal to power our society. And so, the question then, if you decide to access this, is which route generally you take between these two. All right, so that kind of is a review of what we've done. Let me check my time, and I forget what the other one was up to, part A, but I think we're okay on time. And so we have enough time to discuss nuclear power. Which, we talked about there, but particularly its fission. There are no commercial fusion reactors. Perhaps at the end of the course, if we have time, we can go into a more detailed discussion. I can present what I know about nuclear fusion, the potential for nuclear fusion reactors. But currently all nuclear reactors are fission, and basically they produce somewhere around 20% of U.S. electricity. You have to be a little careful with that 20% number because, of course, 20% of electricity is a much smaller fraction of total energy. But yeah, it's something like that, and it has remained that for a few decades now. Nuclear power saw a large increase throughout the 70s and into the 80s. On the other side of the quiz, we will talk more about nuclear power in terms of essentially what's holding it back or what may hold it back in the future. Right now, I'm just going to give you a short tutorial on it, and it will be part of the quiz in the sense that this sort of basic description of how nuclear power works is going to be on the quiz. And I don't need this anymore. So, what you've learned is that if you have uranium, okay, now uranium is primarily U-230. Somewhere around 99%. Okay, let's draw it this way. I mean, it doesn't look like a lump of ore, but this is meant to be what gets dug out of the ground. And the number is closer to 0.3% and 0.7% U-235. All right, so you dig this stuff out of the ground. It doesn't look like rocks. It's called yellow cake. It's uranium oxide that you actually dig out of the ground and sort of purify and you undergo enrichment to make fuel rods that are about 3% U-235. So you take this stuff and you sort of separate out the heavier isotope, and you sort of get the idea that this enrichment process is usually done in kind of a centrifuge, where you gasify, you gasify the uranium oxide, and then you put it in the centrifuges that spin really fast, and basically the heavier isotopes tend to go to the outside, and so you have basically rows and rows and rows of these centrifuges. In every centrifuge you get a little bit of enrichment, and then you keep going like that. Now, if you enrich further, you get so this is a nuclear reactor. This is a reactor fuel rod. If you enrich further, you get a bomb core. Which is about 90% U-235. Now, the reason why I'm not because I'm trying to teach you how to make a nuclear bomb, but just simply it allows us to sort of kind of complete the discussion here, because what happens is that in the nuclear reaction and fission, you are taking U-235 plus a neutron, and that results in U-236. Now U-236 is unstable, so it immediately look at everything. So I don't know, I forget, it's like baryon and krypton usually. Plus 3 neutrons plus energy, lots of energy. Okay, so basically, compared to your chemical reaction, the energy released, and again, it's the same thing, it's because these are more tightly bound than that. That the energy released in this nuclear reaction is like 100 million times more than the energy released in a standard chemical reaction. All right, now, the important thing is this, 3 neutrons. So when this reaction takes place, you have 3 neutrons. And those 3 neutrons can each cause a subsequent reaction. So basically, these, okay, now, before they can cause a reaction, they have to slow down. And then they can make a subsequent reaction. Why do they have to slow down? Well, it's just simple mechanics if you think about it. Okay, this whole thing starts because this U-235 nucleus captured a neutron. Well, it's hard to capture something that's whizzing by, you know, at close to this, well, not, maybe some fraction of the speed of light, which is, you know, the velocities they come out here. And so they have to slow down in order to cause a subsequent reaction. All right, that we can actually make use of that. But getting back to our bomb core, okay, what happens is that, okay, if a neutron from the reaction escapes, it does not cause a reaction, of course, because it's not in the mass. Okay, if it stays in the mass and slows down enough, it will cause a reaction. And so, of those 3 neutrons, if greater than 1 react, okay, then you get a chain reaction. Because if you take 1.1 times 1.1 times 1.1 every fraction of a microsecond, you get an explosion. And so that's an explosion. So I'm not going to get into, you know, how you make this happen, because this isn't a course in bomb making. But basically, there is a critical volume, a critical size, and hence a critical mass, above which more than one of those 3 neutrons both stays in the solid and initiates a subsequent reaction. And if that number is greater than 1, boom. So that's what critical mass means, and you can kind of figure out, you know, how you make that work. But anyway, getting back to our reactor, all right, you make this much less, and the whole idea is you don't want a chain reaction in a nuclear reactor, first of all. So you use this, okay, you make a bed of these things. Now, then you have these screw rods generating a lot of neutrons. All right, and so you adjust things, and there's what are called control rods. I don't want to get into that too much, although that's critical to the operation here. But what I want you to understand is that if you put this whole thing in water, the water moderates the reaction, which means that it slows down the neutrons. Can't spell neutrons. All right. Now, we're going to leave it at that. So you have sort of a basic understanding of how a nuclear reactor works. In a particular, a water-based reactor, okay, how does the water slow down the neutrons? Well, again, it's simple mechanics. Okay, water is primarily protons. And if you maybe remember in one of your mechanical physics classes, things of like size tend to cause the most slowing down. I mean, if you have a great big ball and you throw a little ball at it really fast, it's just going to bounce off and not do any momentum transfer. But if you have something with a lot of protons in it, then that neutron, about the same size, will lose a lot of its energy hitting that water. And so the water slows, it's called moderates or slows down the neutrons. And so you need that. That's called the moderator. You need that in order to make the reaction proceed. Because remember, you have to slow down those neutrons to make them to allow them to react. A fast neutron won't get captured. And so part of the point I'm making is that today, I mean, compared to some other reactor designs, nuclear engineers make use of inherent negative feedback loops so that you avoid a meltdown. Okay, and one of them is that, okay, the water is also used as a coolant for the reactor core. And if you lose water, of course, that's bad because it starts to heat up. But losing the water also loses the moderation, and so it slows down the reaction at the same time. All right, so that's it for up to the quiz. I want to, and it kind of fits in, over there, and so I wanted to include at least the introduction to how nuclear power works. After the quiz, we'll talk more about nuclear power, but more along the lines of, okay, what are the problems with it that have to either be solved or, if not solved, accepted as we, in order to allow it to be used more in the future, which is, again, for your final project, one of the things you will be deciding and explaining why it's the case. Okay, so that's it for today.